Electricity has become indispensable for modern life. We all know these days that electricity can be converted into heat and light. Whether in an electric cooker, a toaster, or in an espresso machine. Wherever there's electrical resistance, something gets hot. This effect was recognized very early on, but why things are as they are, for a long time no one knew. The first to find out was a man who had to struggle for years to be recognized as a scientist. Georg Simon Ohm was born in Erlangen near Nuremberg in southern Germany on the 16th of March 1789, the son of a university technician. The father devoted much of his spare time to physics and maths and gave his sons Georg and Martin intensive lessons in these subjects. From 1800 to 1805, Georg Simon Ohm attended high school. Then, at the age of 16, he enrolled at the local university to study mathematics, physics and philosophy. They were troubled times. While marching on Prussia, Napoleon's troops had billeted themselves on the people of Erlangen. Financial difficulties forced him to drop out after a year and seek work as a tutor in Switzerland. It was 6 years before he returned, but in 1811 he did and embarked upon his doctoral degree. The university authorities allowed him to take his degree without a dissertation, which proved a problem later when he applied for a professorship. At first he found a job as a middle school teacher in nearby Bamberg, but he had set his sights higher. In 1817 he went to Cologne to teach in the Jesuit college. It was famous for the excellent equipment in its physics laboratory. The appliances included some driven by a force which had only recently been tamed: electricity. Travelling showmen had quickly learned how to use it, and serious scientists were also grappling with how to properly describe this new phenomenon and its effects. In 1800, the Italian physicist Count Alessandro Volta had already developed a battery. This made it possible for the first time to generate a steady current of electricity. Before Volta's invention, it had not been possible to conduct proper research into electricity. In 1820, when Georg Simon Ohm started his first experiments in the physics laboratory at the Jesuit college, reputable scientists still believed that the voltage in a battery and the current that flowed through a wire were two independent phenomena. Ohm, by contrast, was convinced that the two must be linked by some physical law. In Cologne, he invested much of his salary in the physics and chemistry laboratories and devoted himself to wide-ranging experiments. In order to test his hypothesis, he passed electrical currents through different wires. He measured the conductivity of each wire using an early form of ammeter, in which a magnetic needle is deflected more or less strongly depending on the strength of the current. He experimented with thick and thin wires, with cables made of copper, silver, brass and various other metals. At first, he was unable to prove the connection which he hypothesized. The reason was that Ohm's source of power was a voltaic pile. The performance of these primitive chemical batteries collapses catastrophically when the poles are connected with too thick a wire. Only after Ohm had developed his own power source, a thermocouple, did his experiment succeed. The new source consisted of a horseshoe-shaped piece of metal with copper rods attached to its two ends. Ohm fixed the ends of his wires to the copper rods. The current only flows, however, when one end of the horseshoe is cooled in ice water and the other is dipped in boiling water. This is because electrons in hot metal have higher energies than those in cold metal. They move faster and try to create an energy balance by streaming towards the cold end. As long as there's a temperature difference, a current will flow. In this way, Ohm, who made all his own equipment, created standard conditions for his researches. And now his surmise was proved right. More current flows through thick wires than thin, and short cables conduct more electricity than long ones. In addition, he made a further discovery. Not every metal conducts equally well. An iron cable, for example, conducts less well than a copper cable of the same length and thickness. The property of absorbing rather than transporting the current, Ohm termed resistance. This resistance causes the conductor to warm up. The electrons flow along the wire. In the process, they bump into the particles that compose the conductor. The more of these particles that get in the way, the fewer electrons can get through, and the higher the resistance of that particular conductor. Every collision slows the electrons down. They lose energy, which is given off in the form of heat. Given the right material, a very thin wire can glow white hot in this way. In the incandescent lamp, this effect is exploited for lighting purposes. The mathematical formula which Ohm derived for this phenomenon he owed to his systematic working method. Ohm entered all his results in his notebooks, recording the length, diameter and material of the wires he used. Over the years, he had gathered so much information that he was able to formulate a mathematical connection and express it as a formula. He discovered that the ratio of current to voltage in a particular conductor is always constant, and he defined resistance as this constant ratio. Today, the formula he derived is known as Ohm's law, namely, resistance equals voltage divided by current. How can we visualize this relationship? The simplest analogy is with a water pipe. The strength of current, or amperage, is defined as the number of electrons flowing through in a given time, analogous to the quantity of water flowing through the pipe. The broader the pipe or the thicker the wire, the more water or electrons can flow through. The potential difference, or voltage by contrast, corresponds to the pressure of the water in the pipe. A lower voltage or lower pressure means less current, whether it's water or electricity. A higher pressure or voltage means more current. At the same time, even at low pressure, you can have very large quantities of water flowing through in any given time. This is the case if the pipe is broad. With electricity, it's no different. The current is stronger. Electrical resistance is a bit like the lime deposit in a water pipe. It slows things down, reduces the current in other words. If the resistance of a conductor is high, less electricity is transported. If it's low, more gets through and the current is higher. When he had completed his electrical experiments, Ohm was granted a sabbatical in the summer of 1826 to pursue his research, and went to stay with his brother in Berlin. Here, the following year, now aged 38, he published his results in a book entitled The Galvanic Circuit Investigated Mathematically. Georg Siemens Ohm knew that he had made a groundbreaking discovery, but he did not become an overnight star. Far from it. The German universities continued to ignore him, although he made intensive efforts to obtain an academic position. Many professors had nothing better to do than ridicule his mathematics. In 1833, after numerous applications had failed, not least because he had never written a doctoral dissertation, he finally obtained a post at Nuremberg Polytechnic, and 6 years later became its principal. His reputation in Germany only took off after foreign physicists, particularly in France and Britain, became aware of his forgotten achievement. In June 1839, the Prussian Academy of Sciences in Berlin made him a corresponding member. 2 years later, he was awarded the Copley Medal by the Royal Society in London, equivalent in many ways to a Nobel Prize today. Now, at the age of 52, his scientific reputation was secure. But his scientific work was not limited to electricity. Success gave him the confidence to look into new fields, in particular acoustics. In 1834, in a treatise entitled On the Definition of Sound, with a theory of the siren and similar sound-producing devices, he described for the first time how the waveform of a pure note is a simple sine curve, and that waveforms of other sounds are nothing but combinations of sine curves. A clarinet sounds different from a piano because the combination of sine curves is different. In this sense, Ohm was the father of modern acoustics. In 1850, he was given the chance of becoming a university professor at last. It was a long-held dream. By now nearly 60 and not in the best of health, he was appointed Professor of Mathematics and Physics at the University of Munich, but he did not have much time to enjoy this belated recognition. Just 4 years later, on the 6th of July 1854, Georg Siemens Ohm died after suffering a second stroke. He was buried at Munich's Old South Cemetery. Years after his death, Ohm received a posthumous scientific honor that was to make his name immortal. In 1881, the International Electrical Congress in Paris established a system of electrical units. Alongside the ampere as the unit of current and the volt as the unit of potential difference, the unit of resistance was named the ohm, with a capital omega as its symbol. Georg Siemens Ohm's researches are remembered to this day. Ohm's law relating voltage, current and resistance is the cornerstone of numerous calculations in electrical engineering. And our everyday lives too, with electricity all around us, would not be so warm and comfortable without Georg Siemens Ohm and his researches.